All right, we're going to do a conducting sphere, just like we did before, but this time we're going to surround it by a neutral conducting shell. So to give you an idea what that geometry looks like, I've got a conducting sphere here um, inside, and then I've filled this space in white, filled it with vacuum, and then I've got a conducting shell. So what you're seeing here, the checker pattern, those are conductors, and then the white is vacuum. Okay? So what I want to do with this is I want to go ahead and set up some Gaussian shapes. I think at this point we should feel okay with the conducting sphere inside. We know that when the Gaussian shape is inside, because all the charges are going to accumulate here on the outside, then we know that the electric field inside here is 0. Let's go ahead and give the conducting sphere a charge of, let's give it plus 2q. Okay, so plus 2q, and then the neutral conducting shell, of course, has a net charge of 0. That's important because we're going to see that because of the conducting sphere here, the plus 2q, the neutral shell is going to have to separate charges, and we can predict the separation of charges using Gauss's law. So this is a really cool application. We've got plus 2q here, so this is plus 2q, and of course they're going to accumulate here on the outside. So here's our plus charges that add up to a net charge of plus 2q. I don't know yet how the charges are going to accumulate on the neutral shell. I'm guessing that there's going to be some negatives that are going to go here because they're attracted to the positives here from the conducting sphere, and then that's going to leave behind some positives on the outside, and that's my guess here, but I don't know exactly how they're going to arrange themselves. Okay, so let's go ahead and draw a Gaussian sphere. Of course, we still have spherical symmetry, so I want to use spheres for my Gaussian shape, and when I draw them inside, okay, when I draw them here inside of the conducting sphere, okay, of course, when the Gaussian shape is inside of the spherical conductor, then the amount of charge enclosed is 0. I've got no charge inside because the charges are going to go out here on the outside of the spherical conductor. Okay, so let me do a couple of things here with the geometry. Let me give some radii here. Let's call this the radius of the conducting shell. Let's call that capital A. To the inside of the spherical shell, let's call that B. And then to the outside of the shell, let's call that C. So those three distances, A, B, and C. So we can say for certain that when R is less than A, when my Gaussian sphere is smaller than the conducting sphere, I know the electric field has to be 0 because I'm inside of a conductor. I'm inside of a conductor. I'm not even going to worry about doing the integral. I know that the electric field has to be 0 inside of a conductor. If I continue drawing my Gaussian shape until right there, now I'm larger than A but smaller than B. So when R is larger than A but still smaller than B, I'm now in the vacuum area. I'm in the vacuum area, and I need to go ahead and set up the surface integral of E dot A is equal to Q enclosed over epsilon naught. Well, at this point, how much charge have I captured? Well, I've got the entire sphere inside. So the entire sphere had a charge of plus 2q. So this becomes E dot A, which is 4 pi r squared. So that's my area of my Gaussian sphere, 4 pi r squared, is equal to a charge enclosed of 2q divided by epsilon naught, and I'm going to divide the 4 pi r squared over, and I get E is equal to 2q over 4 pi r squared epsilon naught, and I'm going to write that as 2kq over r squared. Okay, sometimes for example, on a multiple choice, they might leave it in the 4 pi epsilon notation instead of k, just to kind of throw you off, and they'll reduce this guy, so 2 over 4. They might write one of the answer choices as q over 2 pi r squared epsilon naught. And that's totally still a correct answer. You just need to understand that K and 1 over 4 pi epsilon naught are the same thing. K, the Coulomb constant, is just 1 over 4 pi epsilon naught. Okay? So we have our electric field now in the vacuum space when R is between A and B. Let's go ahead and continue on with our Gaussian sphere. There's another region where things will change over, and that's when I'm inside of the conducting shell. When I'm inside of the conducting shell, I'm inside of a conductor. And again, inside of a conductor, so when R is between B and C. If I'm inside of a conductor, I know right away without doing Gauss's law that the electric field has to be 0. It has to be 0 because I'm inside of a static conductor. Well, now I have an idea of how these charges on this neutral shell must have separated themselves. If I have no electric field inside of my Gaussian sphere, the only way that's possible for the integral of E dot A to equal Q enclosed over epsilon naught. Well, if I'm getting a 0 over here on the left side because electric field is 0, it means that the right side has to be 0 as well. Q enclosed over epsilon naught. Well, epsilon naught is a constant. So it tells me that Q enclosed must actually be 0. So inside of my Gaussian sphere, I must have 0 total charge. If the inner conductor, the conducting sphere, had 2Q, then this neutral shell must have separated itself so that there was exactly minus 2Q on the inner part of the shell. Well, if it's a neutral conductor and charge is conserved, then the net charge on the shell still has to be 0. So how much charge went to the outside of the shell? Well, minus 2Q is on the inner part of the shell, so plus 2Q had to accumulate on the outer part of the shell. That leaves me with a net charge still of 0, but the charges separated themselves on that conducting shell. So the last region that I would need to consider would be finally outside of everything. If I am outside of everything, this is when R is greater than C. Let's set up the surface integral of E dot A is equal to Q enclosed divided by epsilon naught. And let's go ahead and give myself some room here. When R is greater than C, E dot A, again, it's just the area of my Gaussian sphere because of that spherical symmetry. Because E dot A is the same everywhere, I pick up the entire area of the sphere, is equal to Q enclosed over epsilon naught. Well, just how much charge did I capture? Well, there was plus 2Q here, minus 2Q here, and plus 2Q from the conducting sphere. And that makes sense that overall, when I circle everything, the total charge inside is plus 2Q. So Q enclosed is plus 2Q divided by epsilon naught. And I get the electric field is equal to 2Q over 4 pi r squared epsilon naught, which is 2KQ over r squared. So what you'll notice here is that the electric field outside of the entire system is the same as the electric field in the vacuum space between the shell and the sphere. And that's because the neutral sphere has no ability to shield the outer environment from the electric field of the inner sphere. What I'm going to do next in the next video is I'm going to give some charge to this conducting shell, and you're going to notice that the electric field out here is going to be different than the electric field in this vacuum region. That's because when you place charge on this shell, it can either shield the electric field out here, or it can strengthen it if they're the same sign of charge. So we'll see that in the next video. What I'd like to do to close this video out is just graph the electric field as a function of the distance from the center or the radius there. Well, up until part A, we had no electric field because we were inside of a conducting sphere. And then we moved to part B. This was the vacuum region, and in this vacuum region, we had a 2 kq over r squared. So that guy right there is proportional to 1 over r squared. Okay, and then from B to C, again, you were inside of a conductor. You were in the conducting shell, so you had no electric field. And then again, outside of C, and as you move on to infinity, again, it was proportional to 1 over r squared. Okay, so again, proportional to 1 over r squared. But what you're going to notice that I tried to do here is I tried to continue this electric field along the same line of curvature as the 1 over r squared between A and B. And the reason I've done that is these were the same function. This was 2 kq over r squared, and this was 2 kq over r squared, right? We just had this gap in the middle where the electric field was 0 because we had a conductor there, but the electric field before that conductor and after that conductor had the same functionality of 2 kq over r squared. So they should follow the same 1 over r squared curve. Okay, so these are both 1 over r squared. They should follow the exact same curve. We're going to see how this is different when we provide charge to that shell in the next video.